For this topic, I need to use 3 subtopics, B.1, B.2, B.3, to complete the whole story. The first one, evaluate the polynomials. So when we start, all of you know how to evaluate a polynomial, but we want to see what is the best way, what is the fastest way, what is the most efficient way. And also we want to compare the difference, most efficient way and the ordinary way. So here I want to say ordinary way, because most people use that ordinary way. Okay, all right, let's start. Our problem number 2 for this class, evaluate a polynomial. Given a polynomial, you know the polynomial, the definition. Okay, that's the general expression for this polynomial. We have coefficients, n0, n1, that's we call the coefficients. The variable x, single variable x. So the coefficients, when they are given, then we fix it for one polynomial. We fix all the coefficients for one polynomial. But we can change the value of x. Every time when we change the value of x, we want to calculate the polynomial function value at x point. Yeah. The question: how to evaluate P of x efficiently? The fastest possible way. That's our goal. Yeah. Because we may have many different ways to evaluate a polynomial. You may probably only know one, but actually there are more than one. Okay? So which one is the fastest? Okay, all right, yeah. Let's do analysis. All right. Here, the ordinary way I mentioned, everybody knows. When you have a calculator, you know how to find the value of a polynomial. Okay? Basically, you do multiplications and additions. Okay? Yeah. Just the way you use to find the value of polynomial using a calculator, or you write a program, computer program, you can find its value. Okay? Yeah. If we use that way, so here I just temporarily refer as ordinary way. Why we need an algorithm, right? Although that we can treat that as an algorithm, why we need other special algorithm? That's the question. Okay. All right. Yeah. Here whatever way we do, we always need to use addition and multiplication operations, right? Yeah. You can do it in so many different ways, but you need to do additions and multiplications to find its value. Okay? Yeah. Here, how to measure efficiency. Yeah, because here, think about, suppose we have several different methods. We can calculate the value of the same polynomial. Suppose we have more than one, several. The question is, how do you measure efficiency? How do you tell me one is more efficient than the other? That's the question. Okay? Yeah. We want to know that. Yeah. Go there.
You would usually measure efficiency and how much time it takes, right?
Yes, that's the most straightforward measure. Amount of time, clock it. Okay, or in our computer program, we can clock it. There is certain functions we can use to find the time. So that's the most straightforward measure. We can call response time. Response time. We use the response time. That's the first measure. Direct, straightforward measure. Right? Yeah. For the question, yeah, you can use that to compare one algorithm is faster than the other. If I ask you a deeper question, suppose we run those two different algorithms on different computers, not the same computer. Can you still use that way to do comparison? What? Yeah, computer hardware different. One is supercomputer. One is multi-core super 128 multi-core computer. Another is low end. Yeah, very. Yeah.
Or if your computer is pretty good with like whatever your input values are just extremely large in the program. Normally it's very fast for small things, might be very cumbersome with the values of the bigger.
Yeah. So
are you asking the size of the time? What else is there?
yes.
For measuring?
Right.
Measure space?
Right. Yeah. Oh, yes. Space. Amount of space. Yeah. That's we do not call measure. We call it another factor to be considered. Amount of space. Yeah. But not measure. Not measure. All right. Yeah. Precision. Yeah. Precision. Still not measure. Yeah. Still not measure. Oh, so many students. Number. Yeah. Good. Yeah. Very close. You also say something.
Yeah, like comparison.
Oh, yes. You too, the closest answer. Yeah. So another way. All right. So here, this response time, we feel not stable because the hardware factor is important, right? Yeah. Here we don't want to consider the hardware, right? We want to take away the hardware factor, right? So there, another measure that is more stable, more fair, more stable, number of operations, or number of additions, number of multiplications. Yeah. If we use number of multiplications, number of additions, then we don't worry about which computer we use, right? Yeah. Yeah, think about that. So this is another important concept. Yeah, so we will talk about that more. This is the first time we see this question. All right. All right. Execution time not stable. Right? Here, answer, not stable. We want to find a stable, better measure. All right. So here we use the number of additions and number of multiplications, more stable. Number of operations, more stable. Okay, all right. Now let's try it. Let's work on it. Yeah. So for the given polynomial, let's count number of additions, number of multiplications. How about that? Can we do it? Yeah. Counting. Here we need to do counting. In discrete math, you learn the counting techniques, right? Math 3000. Yeah. I try to remind you counting techniques, basic counting techniques, not advanced. All right. Now let's do the counting. The first time we do the counting, the straightforward math algorithm, just multiplication, addition, when you find the value of this polynomial, the normal way. Okay. Yeah. The question: So here, let's consider number of multiplications first. Number of multiplications first. We have many terms. How many, tell me, how many terms do we have in this polynomial? N plus 1. How do you know it's n plus 1, not n? Anybody can explain to me n plus 1, not n?
Because we're including, and like we're including x to the 0.
Yes.
Which is 1, so that make that a to the 0, a sub 0.
Yes.
Right?
Because when we do the counting, we start from 0, not 1. From 0, 0, 1, 2, 3, through n. That's n plus 1 numbers, not n numbers. Okay, yeah. So we have n plus 1 terms. Here, we want to consider a general term. What is the general term? Here, we write the expression of general term. A sub k times x to the kth power. That's the general term, right? Yeah. When k equals 0, that's the first term. When k equals 1, the second term, and so on. So we can use this general term to represent arbitrary term by changing the k number. Okay, yeah. Here, for this general term, we use it as a representative. This expression can represent any term in the polynomial. Yeah. Let's do the counting. In this general term, in order to find the value of this general term, how many multiplications do you need? Multiplications. No addition, so we only have multiplication.
Would it be k plus 1 because you have however many times you're multiplying x by k times, plus you have to multiply it to a, so that would be k plus 1.
Yeah, all right. Yeah. Some of you went through part A, right? Tuesday's class. Definitely not all of you, some of you, right? Yeah. In that class, we learned a strategy. Yeah. When we do data processing, here we do data processing. Okay, we count the number of multiplications. We treat as we do certain data processing. If the data is relatively complicated, here, yeah, because this k can vary, bigger, smaller, relatively more complicated. What strategy in this situation? What strategy we use when we have this kind of situation? We do experiment for the data size relatively small, right? Yeah. We work on the simplest cases. Think about that. That's the strategy we learned in part A. Okay. When we need to do data processing, when we start, we work on the simplest cases first. That's the strategy. Okay. Here, tell me, when k equals 1, how many multiplications do you need to do? K equals 1, only 1. How many? When k equals 1, you have a1 times x. How many multiplications do you need? Calculate. How many multiplications do you need? 1. When k equals 2, you have x squared. How many multiplications do you need? X squared, do you need a multiplication for x squared?
Yes, just one, right?
Oh, it's, yeah, it's x times x, it's multiplication times a is.
2, right? Right? Yeah. When k equals 3, how many multiplications do you need? 6. Just think about one more than this one, right? One more.
So it's that same invariant. The same type.
This time not invariant, it changes. So it's, yeah, it changes, yeah.
Oh,
But there is a rule, okay? Can you observe the rule? We do 3 experiments. K equals 1 experiment. K equals 2 experiment. K equals 3 experiment. Can you summarize some special rule after these experiments? Yes, K multiplications. K multiplications. How effective is our strategy? Our strategy, we start with the simplest cases. That's our strategy. All right. That strategy looks nothing, right? That strategy is so trivial, but effective. Because if I do not mention that, nobody may apply that strategy, right? Think about it's effective. Good? Yeah. Good. All right. So the answer is K multiplications. Okay? Yeah. All right. The reference of this topic, yeah. Here, I give you the reference in the textbook, section 6.5. It's some later section, but it's not too hard. Polynomial, you know polynomial well. And we want to do our project number 1 on this topic. So that's why I start this topic early. Okay, all right. Is your algorithm efficient? So here, the next question. Here, each term, K multiplications, so we can calculate the total number of multiplications. So here the question. Is your algorithm efficient? We don't know, right? Because we only have one algorithm. If you cannot compare it with any other different algorithm, how do you know it's efficient or not? You do not know it's efficient or not. Only one. Only one. So that's the only one we have. Okay? But if you have more than one, then you can answer this question. Okay? Because the second one, you want to see if it's better than the first one or not. Okay? But here we don't have the second one. Okay? If we can find the second one, then we can do comparison. Okay? All right. Yeah. Question. Are we satisfied with the solution? At this point, we may not know it, right? So if I ask you, are you satisfied? Probably you will say yes. Because if that's the only way you can do, if that is the only way you can do.
I'm guessing there's another way to do it.
Yeah, another very smart way, super smart way, super smart way. Otherwise, yeah, why I spend time here, right? Yeah, there is a super smart way. Okay, all right. Let's take a 15-minute break. Okay, we do not know how bad it is. Yeah, we want to see another different way to solve the same problem first. All right, yeah. Next thing we need to do, find the performance number of this algorithm. So what's the performance number? Yeah, here, this concept is not that clear. Oh, do you feel the light this way? Yeah, compare to dark. How about feel okay this way? This way?
I'm good with either.
Good with
I
you.
still vote dark, but
Oh, you know.
My eyes are better.
All right. Yeah. This way. Okay, let's try this way. All right. Yeah. All right. Oh. Yeah. So now that something called a performance number, there is no clear definition here, but we want to compare. We want to use a number, certain number, to describe a fair performance measure. That's something we like to do, some fair performance measure. Here we have addition. We also have multiplications. Can you compare additions with multiplications? Compare apple with pear or different things, right? Yeah,
Yeah.
different objects. You need to compare different objects here. Can we do some conversion between two different objects? You know, use some equation, some.
Yeah, because
All right. Yeah, we need to do that. Yeah, otherwise, how do you compare? One side 100 additions, the other side 45 multiplications. Which one faster? How do you know? Right? Think about that. So we need to find some equalities between those two different operations. Yeah. All right. Oh, yeah, I do not go back. Yeah. So let's do that first. Let's add some assumptions. We need a little more assumptions here. Okay. Yeah. So it is allowed to add a reasonable assumptions. And our assumptions should be very close to the real world cases, real world situation, our assumptions. Here. And our added assumptions should not alter the problem difficulty significantly. We do not change the problem difficulty level. Same difficulty level. Okay? Yeah. 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 All right, so here, this is our assumption. We know multiplication is slower. Yeah, I need to admit that side. Because if I do this side, my remote control is disabled. So that side. All right. So here, everyone of you here know multiplication is much slower than addition in general in computer. So here, not you do multiplication. When computer does a multiplication, it is much slower than addition. But how much slower? We need to know that. How much slower? That ratio here. For addition, because it's faster, so we assume the amount of time for one addition is 1 unit of time. Just 1 unit. Okay, yeah. Here, this unit, certain number of nanoseconds. Because right now, our computer is very fast. So, a certain number of nanoseconds, that level. You know nanoseconds? How fast? Nanoseconds? How big? Nanosecond? 1 nanosecond equals 10 to the negative 9th power of s second. Oh, 1 billionth of a second. 1 billionth of a second. That's 1 nanosecond. Yeah. Okay, yeah. So that's how fast our addition could be. All right. Then for multiplication, it takes 10 units of time. The ratio is 10 to 1 ratio. More precise, but close. Here in our discussion, we make this assumption. This assumption is pretty close to the real world situation, cases. Okay, yeah, 10 to 1 ratio. Now we can compare multiplication and additions, right? 100 additions, you need pretty much the same amount of time as 10 multiplications. Okay, all right. Yeah. So now With this assumption, we do not change the difficulty of this problem. So we should be fine. Yeah. All right. So let's do the work. Now we can count the number of additions, then we count the number of multiplications. At the end, we can calculate the number of units we need. How about that? The total number of time units we need to calculate this polynomial. Okay, all right. First, how many additions do we need? Look at this polynomial. Can you tell me the number of additions we need to do in this polynomial? How many?
It'd be n plus.
It's just n, right? Is you have two,
Oh,
it's the same
yeah.
as before,
No,
like
it's
you have
n.
two factors, one multiplication.
Good.
So,
N. The answer is N. Okay. All right. Yeah. Yeah. All right. But here, when you do the counting, yeah. Because here we also have the dot, dot, dot. When we have dot, dot, dot thing, we have the keep tracking problem. How do you keep track of all the terms with dot, dot, dot? Okay, yeah. Here, when we count the number of additions, one addition corresponds to one plus sign, right? One plus sign. So we only need to calculate the total number of plus signs. Okay, but the question is, how do you keep track of all the plus signs? With the dot, 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 how do you keep track of all the plus signs? Okay, yeah. So here, a better method, try to find some suitable reference. Because plus sign, there is no reference. All the plus signs look the same. You cannot tell difference. But can you associate the first plus sign with the subscript of A1, the second plus sign associated with the subscript of the second term A2, and so on? Can you associate the last plus sign with the subscript of the last coefficient A sub n? One-to-one correspondence, right? That's one-to-one correspondence. For the plus sign, it's hard to keep track of them because they all look the same. How do you tell the difference? How to keep track of? But for the subscripts, is it easy to keep track of all the subscripts? They're natural numbers, all right? Counting from 1 through n, that's n. How about that? Here, this counting method, I call it counting by reference. When you do the counting, you need to find appropriate reference. All right, so here, let me describe this method. Yeah, because later we will use this method many times. Counting by reference. Okay, counting technique. This counting by reference technique. Okay. All right. Essence of this method. We need to discover one-to-one correspondence between two mathematical objects. Yeah, two objects. Okay, one-to-one correspondence. Here, in this example, we have these two objects. Object 1, object 2. Object 1, addition. Object 2, subscript. Think about that. Object 1, additions, plus signs, how to count. How to count. How to keep track of them. Okay? But object 2, easier to count. Easier to keep track of them. Okay? Yeah. We just switch. When we need to count number of object 1, we just switch to counting number of object 2. After we get the answer, that's the same number for counting number of object 1. How about that? Okay, so that's simple method, right? Yeah. So the answer, n units of time. N additions n units of time. The part one, addition part. Part two, multiplication part. Okay, all right. B.2, all right, so yeah, let you see a little bit. Okay, yeah. Then we need to move to the next topic. Okay. Yeah. All right.